of course, we are also interested in the accretion and jet modeling in a simultaneous manner. And the way it has been kind of studied is using the multi-frequency observations. And how this has been studied over the years is that while using the low frequency observations, like of VLA and ARCA, one can study the profile of the spectrum, multi-frequency spectrum, and it is seen that the case of the low luminosity AGNs to be analogous to what is seen in the gigahertz peak sources. And the figure here shows, sorry, the figure on the right shows the spectral index across the 5 to 8 gigahertz observations against the higher frequency path. This shows us how the flat spectrum sources to be unlikely caused by the high accretion rates against the more dominant elliptical galaxies with powerful jets. And in terms of the theoretical interpretation, this could be possibly dominated by the non-thermal electrons within the ADAF, but this and several other constraints are yet to be discussed in further lengths using the state-of-the-art simulations. Just to summarize here and kind of place the roadmap as to how, again, this project is done thanks to, again, by the effort from the external members, is again, making a much robust constraint on the sources that we have on the ether sample. And as mentioned earlier, this was also by taking the stellar dynamics measurements of the black holes, and where not available, of course, the latest state-of-the-art instrumentation is going to give us a much better constraint on the black hole mass. And followed by that, we will also be using sort of VLBI, low frequency VLBI observations, both by the VLBA to the north and the long wavelength array in the south. This will help us study the jet morphology and the compactness of the source, eventually taking great lengths to the ngEHT. And which, again, when it comes to multi-frequency observations, the interest here would be also to study the course shift properties of the jet, and hence to also say study the formation of the collimation profile of the jet. And from the multi-frequency observations, that is using the spectral energy distributions, one can also model the ICDs using the analytical or the GRRT techniques to get more robust constraints of the theory. So this and more work that is currently being tested and will be presented across this conference will be some of the impetus for the next generation efforts, and probably will take the first priority when we get a major breakthrough in terms of the instrumentation for the ngEHT. So I stop here and I'd like to take any questions if there's time, or leave it to the chair.
Thank you very much, Venkatessh. Are there any questions for Venkatessh? Please use the raise hand button or put your questions in the chat. Daryl Haggard, yes.
So thank you for the talk. I'm wondering, I think I know a little bit of this because you and I worked a bit together on these programs, but what do you see as the most important sort of data to acquire right now to support these programs, since we have missions that will be decommissioned by the time ngEHT is around? And what sorts of things, what data sets do we need to build at the current moment?
Okay, well, yeah, that's a good point. Given that the rise of these passive phasing capabilities of ALMA, we believe some of these sources are already going to come into light in the coming years. And yeah, to get more better handle on these sources, I think it's important to narrow the constraints of the accretion properties. Hence to say, again, from the multi-frequency perspective, I think we already have sufficient VLBI information of these sources, at least the most 5 top priority sources. But I think one has to go deeper in terms of the optical and X-ray observations to look for perhaps high sensitivity observations, or where possible where we can detect those ion alpha lines, as I think in the case of Centaurus A might be useful to take it into the theoretical modeling efforts and get much better constraints of the spin and other parameters, which will be helpful for the theorists once they run their suite of simulations.
Thank you. There's a question from Neil Nagar.
Thanks, Sarah. Actually, just a follow-up from Daryl's question, which scared me very much. So I wanted to ask about the GMBA future into the next decade. How certain is it? Daryl, which one were you talking about?
May I answer that?
I think you are the one to answer that.
Well, I am the GMBA European scheduler, but I would say that since the GMBA is based in the functioning of the young telescopes and the VLBA and other European partners, which also work regularly for centimeter wavelength, this is quite secure. Our commitment is there for the next years to keep doing that. Because it's a relatively small effort, 2 sessions of 5 days per year with telescopes which are doing continuously VLBI in any case.
Great. Thank you very much. Let's thank Venkatessh again. Let's move on to our next speaker, Giacomo Fragione, on an upper limit on the spin of SgrA star based on stellar orbits in its vicinity. Go ahead.
Yeah. So thank you for the introduction. So yeah, I'm going to talk about how to place an upper limit on the spin of the supermassive black hole in the center of our galaxy using the information on the stars, on the innermost stars we observe in the Milky Way. So for just to give a brief overview of what we know exists in the galactic center is exactly this picture. Okay, so we have the supermassive black hole sitting in the core of our galaxy, and the supermassive black hole is surrounded by the cluster of innermost stars, the so-called S stars, and this within like a fraction of like a few milliparsecs, so say 1,000 AU. And then we have on larger scales, we have both old and young stars. We have also evidence for the presence of a disk of O and B stars extending up to a fraction of a parsec. We might have like remnants of star clusters disrupted or some putative IMBH over there and molecular clumps. So generally speaking, so we have to take into account 2 fundamental radii in this picture. So the first one is the obvious Schwarzschild radius of the supermassive black hole, that is of the order of 0.04 AU roughly. And the second one is the influence radius of the supermassive black hole, that is around a couple of parsecs. So basically, everything within this influence radius at the lowest order of approximation follows Keplerian orbits around the supermassive black hole, because the dynamics is completely dominated by the supermassive black hole. However, on longer timescales, the interactions among the stars and the compact objects that are in the galactic center tend to drive the orbits out of their Keplerian fixed configuration and make them drift both in energy, diffuse both in energy and angular momentum. So the general picture we have in mind based on dynamical considerations is the following. Okay, so you can see here on the left-hand side, this arrow indicating like longer time scales. So on the the smallest time scale is the orbital Keplerian period. Okay, so here the energy and angular momentum are fixed. On slightly longer time scales, the interaction with the other stars starts becoming important. And over a time scale that is called the vector resonant relaxation time scale, one of the components of the angular momentum changes, while the energy and the intensity of the angular momentum remain constant. So this means that the orbits of our objects change inclination in time. On even longer time scales, the angular momentum changes also in magnitude. So basically, over the scalar resonant relaxation time scale, the orbits of the star change both inclination and eccentricity. And on even longer time scale, on the so-called non-resonant or two-body relaxation timescale, everything diffuses in time, so including the energy. So in this case, also the size of the orbit, so the same major axis of the orbit will change in time. Okay, so this is basically roughly what these timescales are in our galactic center. So as you can see here, these, have, so some nice features explaining some of the things we observe in the galactic center. So now, but apart from these, say, Newtonian considerations, we have on the top of that, that there might be also relativistic corrections to this picture, because the galactic center is one of the densest regions in the universe you observe, with a density of over 1 million solar masses per parsec cube. So, and also obviously in the vicinity of the supermassive black hole, the relativistic effect can become extremely important. So among them, what I'm going to consider is just the correction to the 1.5 post-Newtonian order to the Keplerian equation of motions. So this correction to the orbit is given by only if the supermassive black hole, so if a black hole, in our case the supermassive black hole, is spinning. Okay, so if it's spinning, and we usually parameterize the spin of the supermassive black hole this way, such that chi is anything between 0 and 1, with plus and minus according to prograde or retrograde orbits, and over a timescale it is known as length steering precession or frame dragging precession timescale. The argument of periapsis, longitude of the ascending nodes and inclinations of the stars will change in time. Okay, so since the black hole is spinning, we expect also the possible presence of a quadruple effect, but this happens on timescales much longer than this. And so, I mean, we can neglect, for the moment about it. We can forget for the moment about it. So what I want to stress is that, so basically on the top of your Newtonian changes to the orbit, you have also changes due to relativistic precession due to the spin of the supermassive black hole. Now, how do we use this information? We use it using the well-known orbits of the S stars that, as I told you, are the innermost stars we observe in our galaxy, stars that, have given a Nobel Prize this year. And so these stars are within a couple of thousands AU from the supermassive black hole. Their orbits are somewhat eccentric as well. Their masses are typically between 3 and 20 solar masses, so they are like OB type stars, and their ages are between are the order of 100 mega years. So now, and the fact that we want to use this is because obviously the relativistic effect of supermassive black hole become more important the closer we go to the supermassive black hole. So we have to use the innermost stars we observe in our galaxy to probe these effects. Also because it's like difficult to disentangle this from the many other effects and source crowding we have in that region. So now it turned out that, so these S stars have been known now for more than 20 years, basically. And, but only only basically recently, last year, new observations, new analysis reported that actually these S stars are not distributed isotropically around the supermassive black hole, but they are distributed along two almost perpendicular planes. Okay, so these planes have been labeled red and black planes, disks. So the difference is that, so basically the red plane is a bit more dispersed with respect to the black disk, and the eccentricity it's typically smaller, and this might reflect some other dynamical effects. But the important thing that I want to stress is that these stars are roughly distributed into two orthogonal planes. And to make you realize how these things are, it's like, as you can see here, we have the galactic plane projected over here. And so these angles are about 45 degrees. So they are perpendicular to each other and about 45 degrees with respect to the galactic plane. So now, as I said, we have one of the relativistic effects we expect if the black hole in the center of the galaxy is spinning, it's the length steering precession. Okay, so in particular, we want to consider just the length steering precession of the inclinations of these objects. So now the argument goes as follows. So observations, nature were kind enough to give us two perpendicular planes over young stars are distributed. So now what we can do is we can take the length steering precession timescale, plug in here what the people working, on observations of S stars tell us. what the gravity collaboration tells us, these very unique observations, and we can compute this time scale. Okay, then we can compare this time scale to the basically average age of the stars. So obviously, if the spin of the supermassive black hole is big enough, this time scale basically will be short enough such that the stars, if they are not lying on the equatorial plane of the supermassive black hole, at some point in time they will tend to be dragged over there, and so they will be on the equatorial plane. So now, if we had only one plane, we would have been not that lucky, because, you know, by chance it might have been the case, you know, where the stars were already aligned with the equatorial plane. So basically, this effect given by a cross product will be basically 0.
1 minute.
Yes, thank you. While in our case, we have basically 2 orthogonal planes. So even if this effect might be 0 for one of them in one extreme case, for the other one, this effect will be the maximum. Okay, so basically simply requiring that this time scale is not long enough, let's say it has to be like longer than the average age of these stars, such that they didn't have enough time to diffuse out of their disky configurations, we can put constraint on the spin of the supermassive black hole. And so it turns out that a sort of, let's say, as you can see from this plot, you know, an upper limit can be put to 0.01. So it's like a supermassive black hole spinning at 1% of the velocity of light. So now, obviously, you know, these considerations are, you know, are based on the observations at stars that now we know they are into these key configurations, and is like very unique to our galactic center. But I would like to stress that in particular, future AGNs data analysis and observations can tell us, you know, if our prediction is correct. So if they prove us right, it means that effectively, you know, these S stars are distributed this way we think they are now, so into these configurations. If the further observations prove us wrong, it's also interesting at some level, because it tells us that there are many more stars than we observed there. Okay, and they are not in these configurations, but they are maybe in a more isotropic, distributed in a more isotropic fashion. Okay, so that's it. Thank you.
Thank you very much. We have time for one question. Is there a question for Giacomo? Please raise your hand or type in the chat. Okay, so I have a question. So you said that right now the stars that we have, the S stars, are in this kind of 2-disk configuration. Is there a sense of how many more stars there could be to find that could actually alter this view of this disk? Like, how many more do you need to kind of remove this idea of this 2-disk system?
Yeah, so yeah, that's a good question. You know, so up to now we have like 40 S stars roughly. There are a few more of them for which we don't have like good, let's say, good data. I mean, enough data points to resolve the orbits. But you know, I would say that definitely we would need like roughly, you know, like same order of magnitude, so at least like tens of these S stars to understand exactly, you know, this distribution. But, you know, just to stress that, you know, they are in these configurations, and, you know, we also observe disk of young stars at larger distances. So it's like, you know, very likely that they might have formed over these disks.
Okay, thank you very much. Let's thank Giacomo again and move on to our next speaker. So our next speaker is Jen Pan on the formation rate of extreme mass ratio in spirals in AGN.
Okay, can you hear me?
Yes.
I slightly changed the title. So the new title is Synergy of LISA and ngEHT on observations of M rays. This talk is based on a recent archival paper we posted. Okay. In this talk, I will first give a brief introduction about what are MRAs and where to find them. Then the major part of this talk, two formation channels, the loss count channel and the AGN disk channel. And finally, some brief discussion about the synergy of LISA and next generation ngEHT. Okay, what are MRAs? Usually, MRA consists of a massive black hole and inspiraling stellar mass black hole around it. So according to this definition, is a hydron massive black hole plus stellar mass black hole pair or MRA? The answer is no, because the stellar mass black hole is not inspiraling, and we usually call this system as propter in full. Then where do we expect to find MRAs? The answer is pretty obvious, because we expect to find the massive black holes in the center of galaxies. So that's where we expect to find MRAs. Okay, let's turn to the first channel of MRA formation, usually called loss count channel. On the left, it's a cartoon picture about the massive black hole in the center and some stars and the stellar mass black holes around it. Let's consider one of the stellar mass black holes. For the motion of the stellar mass black hole, there are two important time scales. One is the gravitational wave emission time scale. The other is the relaxation time scale, which is from the scatterings from stars and other stellar mass black holes. Okay. If the scatterings are more important, then the stellar mass black hole will be randomly scattered directly into the massive black hole or scattered away from it. In that case, there will be no stable MRAs. If the gravitational wave emission is more important, then the stellar mass black hole orbit will gradually shrink and finally become a stable MRA. That's a basic picture of loss cone. And the condition for the MRA formation is gravitational wave emission should be dominant. And so for gravitational wave emission to be dominant, we want the distance between the stellar massive black hole and the massive black hole to be close enough, shorter than some critical length scale I listed here. Okay, and the second channel, the MRA formation assisted by AGN disks. Similar to the previous channel, we have a massive black hole and a stellar cluster. The difference is the massive black hole is accreting, so there will be an accretion disk. Now we consider a stellar massive black hole orbiting around the massive black hole. Due to its periodical motion around it, there will be density waves excited on the disk. So the density waves will dampen both the orbital eccentricity and the orbital inclination. Also, the density waves will drive the inward migration along the disk. So in this system, there will be 4 important time scales. In addition to the relaxation time scales, we also have the damping time scale and the inward migration time scale. And the disk lifetime is another important time scale here. So in general, if the inward migration time scale is shorter than the disk lifetime, then we expect the stellar massive black hole will have enough time to migrate to the vicinity of the massive black hole and finally become an MRA. Okay, with the two naive pictures in mind, we can do some serious calculation. Let's first calculate the emery formation rate via the loss count. To describe the stars and the stellar mass black holes in a cluster, we choose their distribution functions f. Usually they are functions of time, energy, orbital energy, and the big R. Big R is a normalized angular momentum. The distribution functions are governed by the famous Fokker-Planck equation. I skip some of the details here. Basically, it's an integral differential equation because all the coefficients are functions of the distribution functions themselves. Given some initial conditions, we can evolve the system and get the distribution functions as the function of time. Okay, here I will show you one example. We consider a SgrA star-like massive black hole under the stellar cluster around it. Given some initial condition, we evolve the system from t equal to 0 to t equals 5 giga-year. And we have the two-dimensional distribution functions of stars and the stellar mass black holes and their corresponding one-dimensional distribution as a function of time. Basically, with the distribution functions, we can get everything we want, including how many stellar mass black holes are probed in fall per unit of time, and how many emeries formation per unit of time. Okay, in the left corner plot, the orange line is the emery rate as a function of time. So roughly, the peak value is about 200 emeries per giga-year per massive black hole. So we did a similar calculation for different massive black holes. We find the typical value of the emery rate has a mild dependence on the black hole mass, but the typical value is about 200 per giga-year per massive black hole. Okay, that's emery rate from the first channel, and let's turn to the emery rate of the second channel. Due to the existence of the accretion disk and the disk stellar mass black hole interaction, we needed to modify the Fokker-Planck equation. Especially, we need a source term S. Actually, it's a negative source term to capture the to describe the stellar mass black hole captured onto the disk. Okay, again, given some initial condition, we can evolve the system using the modified Fokker-Planck equation. Okay, we take the final state of the loss count channel as the initial state of the disk channel. We evolve the system from t equal to 0 to t equals 10 to 8 years. Also, we have the two-dimensional distribution functions and their one-dimensional correspondence. Okay, as a function of time, with the distribution functions, we can calculate the corresponding emery rate where it's assisted by the AGN disk.
1 minute.
So okay. So okay. On the right corner is the emery rate assisted by the AGN disk. So you see the typical value is 10 to the 5th. Okay, if we compare the two channels, we find the disk channel usually is more efficient than the loss count channel by a factor of 10 to 1,000, depending on black hole mass and other conditions. But not every massive black hole is accreting. From the local universe, only 1% of them are accreting, and for higher redshift, the fraction will be slightly higher. Combine these numbers, we expect the disk channel will be an important channel for the LISA and the tangent detectable M rays. Okay, finally, some synergy between LISA and the next generation ngEHT. From LISA, we expect to accurately measure the M ray source properties, including the massive black hole mass and the spin, also some environmental effects, including the disk structure. From the ngEHT, we expect to measure the AGN jet properties, the black hole shadow size, and the disk emission. Combine the two, we can do a lot of things, including related jet properties to the source properties, and we can measure the distance, and from the disk structure plus EM emission, we can accurately measure the accretion physics. Thank you.
Thank you very much. We have time for one quick question. Avery, do you have a question?
Yeah. So hi, Jen. So this is really an interesting idea to use coherent effects to try to change dramatically the diffusion problem. But not only will it be throwing stars towards the black hole, it could also modify the jitter motion that Mark Reed talked about over lunch yesterday. So I was wondering if you thought at all about that. If you're creating density waves in the surrounding disk of stars or the surrounding stellar population, is that going to massively increase the expected amount of jitter or analog of Brownian motion of the central black hole in the galactic center?
Okay, that's a good question, but we in our calculation of the M ray rate, we treat the disk as a background. We didn't consider how the stars or the stellar mass black hole changes the accretion state.
Understood. It might be something interesting to think about.
Yeah.
Okay, thank you very much. We're out of time, so let's thank Jen again. Let's move on to our last talk of the session by Gopa Kumar on OJ287, potential Rosetta Stone for the nascent multi-messenger nano-Hz gravitational wave astronomy. Go ahead.
Can you see my slides?
No, we cannot. We only see a terminal.
Okay, let me just stop here and again try to share. I'm sorry for the delay. It's there. Just can't. It's too late here in the night, so but I will try again.
No worries. Yes, we see the slides.
Okay, thank you. Let me just do the full screen. Okay, well, very early good morning from here. You can hear me, right?
Yes, but it seems the screen is frozen.
Okay, I will, okay, let me see.
We don't see the full screen view.
Okay, so now you can, it's not frozen, right?
Can you try to switch slides?
Yeah, is it okay?
It's frozen.
Oh my God. It says sharing is, I have no idea what's going on.
Can you try to share desktop? Maybe that will work.
That's what I did. I apologize. Again, this is crazy. It never happened.
Yes, now we see the full screen view.
Okay, thank you.
It's a couple of slides in. Yeah, I can see you flipping it.
Okay, so let me first give you a short summary of what I'm trying to do for in this talk. It has been already mentioned that bright blazar OJ287 is the most promising candidate for hosting a nano-Hz gravitational wave emitting massive black hole binary. And this is essentially because of observation of certain optical and infrared flares for the last 15 years or so. And these are predicted based on a general relativistic description for the blazar OJ287. And we are hoping that the ongoing and planned radio observations of the source should allow us to unveil, an object to pursue multi-messenger nano-Hz gravitational astronomy. And this will have implication for ngEHT, hopefully with an Himalayan submillimeter wave observatory. Okay, so why are we confident that this is indeed a binary black hole candidate? Well, it's a quasar. It's around a gigaparsec. As Sara mentioned, that it's actually in the ecliptic. It's been accidentally photographed. So you have optical light curves dating back from 1891. So if you give a look at the light curve, you actually see, there are these flares which last around a year, and those amplitude of those flares actually vary on a time scale of 60 years. But when you look at these flares, and in the recent past, they've been able to zoom into that, and then they see flares which are roughly last for a few weeks, and they are double peak in structure, and they repeat around 12 years. So that's the observation. Mori and his collaborator, Harry Letto, suggested 25 years ago that, well, there can be a supermassive black hole binary to explain those observations. So the idea is that you have a big black hole and accretion disk around it, and then slow accretion of gas onto that black hole, make it visible. That's what we see as OJ287, the blazar. But the OJ287 blazar is actually orbited by another massive black hole, and it regularly plunges through the accretion disk twice every orbit, and it causes the gas in the disk to heat up dramatically, and that will radiate for weeks. That will be thermal Bremsstrahlung in comparison to the regular radiation you expect from a blazar. So this essentially allows you to explain quasi-periodic doubly peaked high brightness flares. So that's the cartoon we have. So you have the big black hole surrounded by the accretion disk, and you have a small binary black hole orbiting it, binary black hole orbiting it. And it's a fairly compact system, so roughly 0.2 light year in the extension. So it turned out that if you have timings of 6 peaks, you should be able to find a solution for a binary black hole model. That's easy to argue. So it turned out that in 2005, they were able to close the orbit. It's around, in that case, the total, the mass of the primary turned out to be around 18 billion solar mass, the secondary around 100 million solar mass. It's an eccentric orbit around 0.6, orbital period around 12 years. So if you put that in general relativistic arguments, the advance of perihelion advances 40 degrees per orbit. But important thing is that in the simplistic picture, you are allowed to make a prediction if this is the correct. So they made a prediction that the next flare should happen around 13th of September 2007, and that did happen, and it was observed within a few days of accuracy. And so the interesting thing about this is that general relativistic equations were used, and if you emit the effects of gravitational wave emission, then the outburst should have been predicted to happen somewhere in early October. So that's where I was drafted into this project. So because Mori was using post-Newtonian accurate equation of motion, so we went and sort of cleaned up the description a bit. So the idea is that you use post-Newtonian accurate equation of motion to describe the trajectory of the secondary black hole around the primary. So Post-Newtonian gives you correction, in terms of the small parameter V over C squared. And so we actually list them in separate batches. The first line is so-called the conservative contribution, which allows the orbit to precess. The second one is because of the radiation reaction effect. The other one is, the last one is because of the spin effects. So we actually incorporated the spin orbit coupling some 10 years ago and made a prediction that the next flare should happen somewhere in 2015, later part of 2015. And this was followed with lots of observatories. And the predicted flares start happening around general relativity centenary time and peaked around 5th of December. But there was SIFT observation, and there was some polarization, optical polarization data from the ground-based optical telescopes. So we could actually argue that indeed this has a thermal component. It was allowed us to make a estimate for the spin of that primary black hole. Again, so we had now another fixed point of the orbit. So we were able to make another prediction for the next one. So this is essentially the trajectory I've been talking about. You can see that this is X and Y component of the trajectory. It's very compact. You can see that the prediction started 2005. There was the 2007, and then you have the 2015. So the flares will not happen when the black hole passes through the accretion disk. There are delays which are incorporated into the model. Most importantly, we were able to argue that the 2019 expected flare should look barely similar to 2007 flare, which were monitored. And because many of the parameters were fixed, we argued that the next flare should happen on July 31st. But unfortunately, the solar elongation was around 10 degrees, so we could not do it from ground. So we asked the Spitzer Observatory to make observations, and that did happen. And so this is so since we have a prediction and we argued that the flare should look like the one we saw in 2007, we could make a comparison of both the channels of Spitzer. That's what's been shown here. Of course, we have to argue slight changes in the fluxes because we are doing this in infrared wavelength rather than the optical one. So, and we could do very systematic analysis to say that indeed we saw the flare. And so if you do that analysis carefully, we could argue that the flares happened few hours within the error bars. We call this as Eddington flare.
1 minute.
Yeah, sure. So we could, this allowed us to argue that there is a spinning massive black hole binary in the system. These days, we are actually trying to make prediction for GMVA observation. The idea is to make prediction for the expected position angle. And this is what José and his collaborators helped us to clarify. So we have actually make prediction using the parameters from the optical observation model and make prediction for GMVA. It looks like the predictions we are made for the 43 gigahertz, 86 gigahertz are being checked with the GMVA observations. This was pointed out by José too. So now the question, as Sara pointed out, if this is a binary black hole of that characteristic, we should be able to see gravitational wavesum. So we are getting involved in that kind of computations. So we are getting into the IPTA consortium, the Indian pulsar timing array efforts. What we do is actually model the expected pulsar timing array residuals from OJ287, systems like OJ287. So that's what, unfortunately, right now, it's very difficult to see them. However, in the SgrA era, that should be possible. So that's essentially the conclusion. The predicted flares of 2007, 15, and 2019 allowed us to argue for the presence of a spinning massive black hole binary in OJ287. We are now trying to do GMVA observation to substantiate that claim. And hopefully ngEHT should be able to, sort of image the binary black hole if there are secondary black hole is active. and hopefully a millimeter observatory in Himalayas will be very useful for that. And of course, that will allow us to do, if we can pick up gravitational waves, you will be able to do a persistent multi-messenger nano-Hz gravitational astronomy with OJ287. And thank you for the privilege of your time. So if you, once you establish that, you get a very unique source to test GR. You can see that in this potential versus the mass log-log plot, OJ287 is in a very sweet spot, not easily attainable from other sources. I think that's all I want to say. Thank you very much.
Thank you very much. We have time for one quick question before the session ends. Is there a question? Please raise your hand. There's no question? Okay, I can ask one. So you mentioned that you do the optical modeling for the jet position angle, and José actually showed this image with GMV plus ALMA of the OJ287 jet from 2017. How does that compare to your model?
Oh yeah, we are in it together. So that's precisely I showed you earlier. So those are unpublished for the time being. So José and his collaborators give us the PA data for the 86 gigahertz. So we had a model based on 15 and 43 gigahertz. So we could actually, use those inputs and some delay expected and make prediction from, for the last few years. So that turning out to be compatible with the observations. So this is a very specific model, essentially Blanford Payne kind of scenario where we monitor the direction of the jet influenced by the binary black hole and the inner part of the accretion disk. And that seems to be consistent with observation.
Great, thank you. So let's thank all our speakers again and close the session. I think there's a coffee break until the half-hour mark, and then we return to the plenary. So thank you, everybody.
Thank you, Sara.
Thank you very much.
Thank you.
Thank you, Sara.
Bye.